Hi, this is Dr. Bricker here with some hints for homework number 6, which is essentially over chapter 10. Let's get into the problems. Okay, the first one we have is 10.1, and we have a 1 kilogram book lying on a table, which is 0.76 meters high. You pick it up and place it on a bookshelf 2 meters above the floor. Okay, during the process, how much work does gravity do on the book? And part B, how much work does your hand do on the book? Let's sketch this out. Okay, so here's the book. It's on a table, 0.76 meters from the ground, and we want to lift it up to a bookshelf, which is up here 2 meters above the ground. So really we're moving the book through a distance of 1.24 meters, the difference between this and this. And the book has a mass of 1 kilogram. So we want to figure out the work by gravity and the work by the hand. Okay, so we're assuming that we're just moving this at a constant velocity the whole time. Here's the free body diagram, force by the hand, and the weight here, which is equal to mg. And we're moving it this direction. Okay, so on the way up, you're moving it this way. On the way up, gravity is this direction. So it's moving this way. The force of gravity is this way. The work by gravity is going to be negative. So whenever the force is in the opposite direction of the way you're moving it, the work is going to be negative. So in this case, gravity does negative work when you're lifting it up. Now, if this thing were falling, gravity's down, then the work by gravity would be positive. So friction always does negative work because friction's always opposing the direction that you're moving. Okay, so the work by gravity is going to be the force of gravity, which is the weight. I'll just call it weight. The work by gravity would be the weight, and then the distance that we're going through. And I know it's negative because, again, we're moving one way and it's back the other way. Now, when you read through the chapter, it might look something like this. So this is maybe a more solid way of writing it. Weight, distance that you're going through, cosine of the angle between the force and the direction that you're moving. So cosine of 180, and then that's where the minus sign comes from. But if you realize that they're completely opposite each other, the distance you're going through and the force, then you can, insert the negative sign. Really, it's coming from this. Okay, so we've got negative mg times d. And this is the d that I'm talking about, the distance that we actually go through. So the work by gravity will be this. As far as units go, here the weight is going to be in newtons. The distance that you're going through is in meters. And a newton meter is a new unit that we have called a joule. Okay, so you've seen that when you've read through the chapter. The work by the hand, in this case, is the force from the hand, distance that we're going through, and then if you want to, cosine of 0 degrees, because those are actually lined up with each other. I typically don't write cosine of 0. I just know if they're in the exact same direction, the work is going to be positive. And in this case, I know that the force from the hand, from my free body diagram, I'm assuming that this isn't speeding up, is equal to the weight. So weight times d. So whatever you got for this part, you get the same magnitude here. It's just that it's positive. So you need to put the negative sign in here and no negative sign here, and both measured in joules. Let's look at the next one. Okay, so 10.6, a crate slides down a ramp that makes an angle of 20 degrees with the ground. To keep the crate from sliding too fast, Paige pushes against it with a force of 64 newtons. And then how much work does Paige do as the crate slides 3.1 meters down the ramp? Definitely need a sketch for this one. Okay, so here's the incline, 20 degrees. Paige's force is 64 newtons. So this is a free body diagram. I don't know whether or not there's friction involved. They don't tell me. But I just want the work by Paige, so I don't need to know how much friction is. You'll see why in just a minute. So this may or may not be the complete free body diagram. Again, we don't know if there's friction back this way. But we have normal force, weight, force by Paige. I just called it force P. And the crate's going to slide this way Page's force is this way. So based on even the last problem that we did, the work by Page is going to be negative. So the work by Page, force of Page, distance that we're going through, and then if you want to, cosine of 180. Again, I usually just remember if the force is one way, you're moving the other, the work's going to be negative. But this is okay. I mean, you'll still get the negative 1 for that. Cosine of 180 is negative 1. So minus, that's the cosine of 180 part. Force from Page, 64 newtons. And then the distance that Page's force is over, 3.1 meters. And then, again, we have a Newton meter, which is a joule, and the work turns out to be negative. Excellent. Okay, so here's 10.11. How fast would a 73 kilogram man need to run in order to have the same kinetic energy of a 8-gram bullet fired at 390 meters per second? Okay, let's take a look at this. Okay, so the mass of the man was 73. How fast would the man have to run to have the same kinetic energy of a bullet if the mass of the bullet is 8 grams? So divide by 1,000, move the decimal point over 3 spots. You get 0.008 kilograms if the bullet is fired at 390 meters per second. So kinetic energy, I usually use Ke for kinetic energy to distinguish it from other Ks that you might see. So Ke of the bullet would be 1/2 mass of the bullet, velocity of the bullet squared. So you can get the kinetic energy of the bullet, and just like work, kinetic energy is measured in joules. So figure out how much kinetic energy the bullet has, and use that over here to figure out how fast the man would have to move, because they're saying the kinetic energy of the man is equal to the kinetic energy of the bullet. So this is a lot less massive, traveling really fast. More massive, going to be traveling slower. They could have the same kinetic energy, though. Okay, so use this kinetic energy over here. And then again, the kinetic energy of the man, 1/2 mass of the man, velocity of the man squared. And then you can solve for the velocity of the man. You probably see that the man doesn't really have to even be traveling that fast to have the same kinetic energy of a bullet, because the man is so much more massive. Okay, the next one is number 12 from chapter 10. Sam's job at the amusement park is to slow down and bring to stop the boats in the log ride. And you can review pages 293 to 295. If a boat and its rider have a mass of 1,200 kilograms and the boat drifts in at 1.4 meters per second, how much work does Sam do to stop it? Okay, let's draw this out. Okay, so the mass of the boat, 1,200. Initially, it's traveling at 1.4. When it stops, it's not traveling anymore. How much work does Sam do? Okay, so remember, work is F D, cosine of the angle between F and D. The new part here is that this gives you the change in kinetic energy. This is the work energy theorem that we see here. This would be kinetic energy final minus kinetic energy initial, 1/2 mv final squared minus 1/2 mv initial squared. So in chapter 9 we had the impulse relationship where we used force, mass, velocity, and time. The work energy theorem is good when you have force, mass, velocity, and some distance that you're going through. Now this one we're not given the distance, but we're just asked for the work based on the change in kinetic energy. So all these different parts are equal to each other, and they're asking for the work that's done. So let's see, work is equal to the change in kinetic energy. Okay, that's good. I can get the kinetic energy because I'm given the mass and the speeds, so I can really utilize this part of the equation. So the work here is going to be 1/2 mv final squared minus 1/2 mv initial squared. And then I know everything. I mean, this term's actually 0 because the final speed is 0, and you can see that the work is going to turn out to be negative, which it should. Sam is slowing this log ride down, so the work's going to end up being negative. Okay, excellent. Okay, number 10.16. The lowest point in Death Valley is 85 meters below sea level, and the summit of nearby Mount Whitney has an elevation of 4,420, above sea level. what is the change in potential energy of an energetic 65-kilogram hiker who makes it from the floor of Death Valley all the way to the top of Mount McKinley? Okay, let's do this problem. So I have a picture here, not drawn to scale. This is just to remind us what gravitational potential energy is. So we're going here, which is 85 meters below sea level, up to this point, 4420, above sea level. And we want to know the change in gravitational potential energy of a hiker whose mass is 65 kilograms. So gravitational potential energy is mgy. Now with gravitational potential energy, you can set the 0 point to wherever you want to. I could say this is where gravitational potential energy is 0. You know, at the down here in Death Valley. And up here, you know, it's all relative. It's relative to this spot. How much potential energy do I have? I could very well say that this is where potential energy is 0. And then down here, it would be negative. Up here, it would be positive. I'm really looking for the change. So it doesn't matter. The change is going to be the same regardless of which way I set it up. I'm going to do it like this because I like to have a 0 spot. Then in the calculations, it's a little bit easier. So the change in gravitational potential energy would be the final gravitational potential energy minus the initial gravitational potential energy. And the initial potential energy is 0 if I'm saying that that's where it's 0. Okay, so this term is 0. So the change in gravitational potential energy would be mg and then y. I'll just call it y final. And by y final, I mean this distance. Okay, draw it over here. All the way from the bottom to the top. This is y final. So you'll have to get that distance. It looks like 4505 or something like that. So figure out what this distance is. You know the mass. You know g is just 9.8. So let me put this in here just to emphasize. This is just the magnitude of g. You don't have to put negative 9.8 or anything like that. Okay, and then again, I think this looks like 4505 meters. Okay, so we're gaining gravitational potential energy. This is coming out positive. As far as units go, we have a kilogram meter per second squared. That's a newton. So this whole part gives you a newton times a meter, which is a joule. Okay. Okay, 18. The world's fastest humans can reach speeds of 11 meters per second. Again, you can review those pages. In order to increase his gravitational potential energy by amount equal to his kinetic energy at full speed, how far would the sprinter need to climb? So let's just talk through this one. So we're going to be setting the kinetic energy that a human has, you know, assuming 11 meters per second, to the gravitational potential energy, and figuring out how high the person would have to climb. The strange thing that might seem like this in this problem is we don't know the mass. You know, on second thought, let's actually write this out and see what happens to the mass. Okay, so there's a certain amount of energy a runner has traveling at 11 meters per second. What if we were able to take all of that kinetic energy and turn it into gravitational potential energy? How high above the Earth's surface would this runner be? So we're taking the kinetic energy, setting it equal to gravitational potential energy. It might seem a little worrisome we don't know the mass yet, but you'll see that it actually cancels out. So kinetic energy is 1/2 mv squared. Gravitational potential energy is mgy, and then you can see what happens to the mass. You don't need to know what the mass is. So we're looking for how high would we have to go. Okay, so I'll leave it at this point. If you have everything, you can figure out how high this person would be able to go if, in fact, all the kinetic energy were turned into gravitational potential energy. Okay, so this one, 1023, the elastic energy stored in your tendons can contribute up to 35% of your energy needs when running. Sports scientists have studied the change in length of the knee extensor tendon in sprinters and non-athletes. They find on average that the sprinters' tendons stretch by 41 millimeters and non-athletes stretched by only 30 millimeters. So the idea here is sprinters, athletes can store more energy in their tendons. The spring constant for the tendon is the same for both runners, 33 newtons per millimeter, What is the difference in maximum stored energy between the sprinter and non-athletes? Okay, let's take a look at this. Okay, the stretch for the sprinter is 41 millimeters. It makes me a little queasy to see this millimeters, so let me put it in the meters right away. Move it over 3 spots. So 0.041 meters. Same thing with the next one. Move it over 3 spots. That's dividing by 1,000. So 0.030 meters. Same thing here. We know it's 1,000 millimeters per 1 meter. The millimeters cancel out. And, 33,000 then. Newtons per meter. So that's the spring constant, K. It's different than kinetic energy. That's why usually with kinetic energy I write Ke. With spring constant I write K. Okay, so what we're dealing here is spring potential energy. So just in general, spring potential energy is 1/2 kx squared. So the K is the spring constant. X is the distance that the spring is stretched from its relaxed position. So if you have a spring here, this is just its regular length. You stretch it out to some distance here. That's the X that we're talking about. You could stretch it or compress it. X is the amount that it's stretched or compressed. Okay? So the spring potential energy of the sprinter, and we're only using 35% of it, would be, sprinter, 0.35, 1/2 K, and then how much the we have here, 0.041 meters. And don't forget to square it. Then you have the spring potential energy of the non-athlete, so I just called it N for non. 0.35, and then 1/2 K, and then how much that's stretched. 0.030 meters. Don't forget to square it. And we're looking for the difference in stored energy. So once you get these values, you can take the spring energy the sprinter's energy minus the non-athlete's energy. That's the difference in energy. So far in this chapter we've had kinetic energy, gravitational potential energy. Now we've got spring potential energy. It's energy that you store for later. So these sprinters and non-athletes are storing energy in the tendon this way and using it later, to propel themselves down the track. Okay, number 25. Mark pushes his broken car 190 meters down the block to his friend's house. He has exerted a force of 120 newtons horizontal push to the car at a constant speed. Okay, great. How much thermal energy is created in the tires and road during the short trip? Okay, so it's another kind of energy that we haven't talked about. It's thermal energy. So in this chapter, thermal energy is completely due to the work done by friction. So the car's going down the block. Mark has a force applied to it of 120 newtons. This thing should be speeding up. It's not constant speed. So there must be friction back the other direction, allowing for no net force. So whatever work friction does, that's the change in thermal energy. Let's take a look at this. Okay, so again, when they say thermal energy, they want the magnitude of the work done by friction. So the work by friction is always negative. Thermal energy, in this sense, they're asking what's the magnitude of that work done. So we've got a distance of 190 meters, force by Mark is 120 newtons, and the constant speed. That tells me that the force by Mark here in the free body diagram is got to be equal to the force of friction. Okay, so if we could find out the work done by Mark, that's the same thing magnitude-wise as the work done by friction. So let's do that. Let's figure out the work by Mark. Mark is pushing this way. The car is moving this way. The work by Mark is going to be positive. So force by Mark times the distance that we're going through. We know both of those. So we have the work done by Mark. So whatever you get for this, the work done by friction is the opposite of that. I mean, technically speaking, the work done by friction is always negative. But then thermal energy is just the magnitude of the work done by friction. So when you get the work by friction, we just want the magnitude of it. So we started with no thermal energy, and we're going to end up with some thermal energy here. So they're actually asking for the change in thermal energy. So it's the thermal energy that we actually calculate here because we started with nothing. So whatever you get here, this thermal energy minus 0 because we started with none. Just be careful, they want the answer in kilojoules. This will come out in joules. To get to kilojoules, divide by 1,000, right? Because 1,000 joules per 1 kilojoule. Okay, great. So again, whenever you see thermal energy in this chapter, it's the magnitude of the work done by friction. Okay, so for 1028, a boy reaches out a window and tosses a ball straight up with the speed of 10 meters per second. The ball is 20 meters above the ground when he releases it. Using conservation of energy, find the ball's maximum height above the ground and the ball's speed as it passes the window on its way back down. Okay, so you could almost do this, well, you could do this with kinematics. Luckily, we have conservation of energy, which will actually make the problem a little bit easier. And then we also want to know, in part C, what is the speed right before it hits the ground. Okay, let's sketch this. So here's what the picture looks like. We're 20 meters above the ground. The kid throws the ball up with initial speed of 10. We want to know how high it gets here, what's the speed when it comes back at the same level, and then what's the speed right before it hits the ground. So again, you could use kinematics to do this. We could use energy conservation. So for part A, whatever energy I have here at this point has got to be equal to the same total energy I have up at this point. So why don't I just call this one like E1 and E2. So E1 is made up of gravitational potential energy. So I'll just call this gravitational potential energy 1, right? Because it's got some distance above the ground. Plus it's got kinetic energy at position 1. Now at position 2, it's not moving anymore. So there's no kinetic energy up here. It's just gravitational potential energy at position 2. And then I can set those equal to each other. So I'm really balancing my checkbook here. I have a total amount of energy here. It's the same amount here. It's just changed forms. So I've got gravitational potential energy 1 plus kinetic energy 1. That's E1. And then that's equal to E2, which is just made up of gravitational potential energy. Good. And I'm trying to figure out this height up here, this Y. So let me take a couple steps further. I have mg times 20 meters. That's the that's the gravitational potential energy I have at this spot, plus 1/2 mv initial squared. That's the kinetic energy I have at this spot, and then that's equal to the gravitational potential energy I have up here, which is made up of mg and then this height, which would be 20 meters plus y. And then you'll see there's a mg 20 meters and mg 20 meters. Those will end up canceling out. Let me just do one more step, actually. mg 20 meters plus 1/2 mv initial squared is equal to mg 20 meters when I distribute this through plus mg y. And then each of those goes away. And then the only thing that you don't know is y. Okay, and you can see that the masses are actually going to cancel out. Okay, good. So you could have done it with kinematics if you wanted to. Maybe it would actually be a little bit faster with this one, as long as you remember kinematics equations. I always remember conservation of energy, though. So that's part A. Part B is, well, if you go up at 10 meters per second and you come back to the same spot, well, you've got to have the same energy you had here if you're heading up as when you pass the same spot heading down. So if you go up at 10 meters per second, there's no air resistance. When you come back through, the speed is the same thing, 10 meters per second for part B. Whoops. 10 meters per second, because you're passing through the same spot. Okay, now the last part, E3, let me just say E3 is when you hit the ground. Same idea. E1, we know that's equal to E2, that's equal to E3. It's just, again, changing forms. So you could, pick any spot you want to. Let's use this one, maybe, now that we know this height here. So at E2, it's all gravitational potential energy, mg y plus 20 meters. That's the height here, 20 plus y. it's all gravitational potential energy at 2. And then at 3, it's all kinetic energy because we're back on the ground. So 1/2 mv final squared. Okay, so we're taking the total energy up here at 2, which is all gravitational potential, and turning it all into kinetic here right when we're back on the ground. And then the only thing that you don't know is this final speed. Okay, you could have used E1 is equal to E3. I just used E2 was equal to E3 for fun. Okay, excellent. Okay, 10.30. What minimum speed does a 130-gram puck, so again, we're going to have to put that into kilograms, need to have to make it to the top of a frictionless, all right, that's good, frictionless ramp that's 6 meters long and inclined at 20 degrees. So another energy conservation. We're taking kinetic energy at the bottom and completely turning it into gravitational potential energy at the top. So how fast do we need to be moving at the bottom to get a certain amount of gravitational potential energy at the top? Okay, let's sketch this. Okay, so here's my incline. This is 6 meters long. This angle is theta, 20 degrees, the mass of the puck. So how fast do we have to be going here to be able to make it all the way up here? Okay, so again, you could try kinematics here. You'd have to, use g, some component of g as the acceleration, figuring out, with that acceleration, how fast you would be going to travel through this distance. We could use energy conservation. So let me call this E1 here, and this E2 up here. So the total energy at E1 is going to be equal to the total energy at E2. The energy at E1, it's just kinetic energy because I'm saying that this is where there's no gravitational potential energy. And then at E2, to make it to this height, we've exhausted all of our kinetic energy, so we're not moving anymore at E2. So then we have all gravitational potential energy. So I'm taking 1/2 mv squared, that's the kinetic energy here, and turning it completely into gravitational potential energy, mg, and I called it h up here. Okay, again, the m's cancel out, and you should be able to figure out the speed. Be careful, you'll have to use a little bit of trig to get this height. Excellent. Okay, so 1033, a 12-kilogram runaway grocery cart runs into a spring attached to the wall with a spring constant of 220 newtons per meter, and the spring is compressed by 65 centimeters. What was this cart's speed just before it hit the spring? Neglect any friction. So this problem would never happen at Aldi's, because at Aldi's you've got to pay 25 cents for a cart. There's no runaway carts. So this is some other grocery store with a runaway cart. Let's sketch this. Okay, so here's the runaway cart moving this direction with some speed. We don't know the speed. It's going to hit the spring and compress the spring by some distance x. So we're taking the kinetic energy of the cart and turning it into spring potential energy here. So another energy conversion. E1, all kinetic. E2, what happened to all this kinetic energy? Well, it turned into spring potential energy. So E1 is equal to E2. So right before it hits the spring, it's all kinetic energy. And then now it hits the spring, compresses the spring. What happens to that energy? It becomes spring potential energy. So I'm taking my 1/2 mv squared energy and turning it into 1/2 kx squared energy. And then the only thing that you don't know is the speed. So this is a complicated problem. I mean, once the cart hits the spring compresses. The more and more it's compressed, the bigger and bigger the force. You can't even use kinematics because you don't have a constant acceleration. So you really have to use energy conservation here. You just want to know what happens at this instant, what happens at this instant. You don't need to know what's going on while the spring is being compressed, just the endpoints. Okay, 1/2s cancel out. The only thing, again, that you don't know is the speed. Okay, a hockey puck is given an initial speed of 4.9 meters per second. Okay, great. If the coefficient of kinetic friction, okay, so we got to think back to chapter 5, coefficient of kinetic friction between the puck and the ice is 0.05. How far does the puck slide before coming to rest? Okay, so you know initially how fast it's going. When it comes to rest, its speed's going to be 0. And it says solve the problem using conservation of energy. Okay, let's take a look at this. So here's what I know. The initial speed is 4.9. Coefficient of kinetic friction is 0.05. And the final speed is going to be 0. Here's the free body diagram. Normal force, weight, and then we've got kinetic friction back this way. It's kinetic frictional force that's going to actually slow us down. I'm assuming that we're moving this way. And we want to know how far we slide. So again, it's the kinetic friction force that's going to enable this thing to actually stop. Just as a reminder, kinetic friction is the normal force times mu sub k. In this example, the normal force is equal to the weight, so mg times mu sub k here. Okay, so we want to use energy to solve this. So the work done by friction, that would be the force of friction, d, and don't forget there's a minus sign there because the work by friction is always negative. The work by friction is going to be equal to the change in kinetic energy, the work energy theorem. And the change in kinetic energy here is 1/2 mv final squared minus 1/2 mv initial squared. So it's a problem where I have forces, velocity, distance. So I think work energy theorem. Usually you think about mass too, but maybe the mass is going to cancel out. We're hoping it is. We're not given the mass in this problem. I don't think so. We're going to have to, play along and see if it cancels out. Okay, so work by friction, force of friction times d, there's the minus sign. That's equal to the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared. And then the final speed is actually equal to 0. So let me clean this up a little bit. So force of friction times the distance that we're going through equal to the change in kinetic energy. The first term here is actually 0, so minus 1/2 mv initial squared because this term is 0. Good, so the 1/2s actually go away. Good, so I'm trying to figure out this distance that we're going through. In the chapter, there's no distance that a puck goes through formula. We've got to rely on our concepts to solve this. And then I know what kinetic friction is from over here. It's mg mu sub k times d. Remember, that's what kinetic friction is. And then I added the d in. So kinetic friction is this part of it. And that's equal to 1/2 mv initial squared. And then the m's actually do cancel out. And you can go through and then solve for the distance. Okay, so just a couple more to go. Ball 1 with a mass of 130 grams and traveling at 12 meters per second collides head-on with ball 2, which has a mass of 320 grams and it's initially at rest. Okay? So when you read through the chapter 10, there's a part with that deals with collisions and kinetic energy. We talked about it in chapter 9 with the momentum chapter, but this also takes into account energies. And we want to know what is the final speed of ball 1 after the collision. If it's perfectly elastic, okay, that means the momentum before and after is equal to each other, of course, but it also means that the initial kinetic energy of the system is equal to the final kinetic energy of the system. What's the final speed of ball 2? And then C and D, what is the final velocity of ball 1 if the collision is perfectly inelastic? So you have to think back to chapter 9 for that. That just means sticks together. And then what is the final velocity of ball 2 if the collision is perfectly inelastic? Okay, good. So part C and D, it should be the same value. What is the final velocity of 1 if the collision is perfectly inelastic? So any perfectly inelastic means sticks together. So if they're stuck together, the answer for C and D will be the same. So, review chapter 9 for that part. But let's take a look at part A and B. So luckily, the author of the book has solved some equations for us. So with this kind of collision, mass 1 is going to the right, mass 2 is stationary. So for momentum, the initial momentum is equal to the final momentum. But we also know that the initial kinetic energy is equal to the final kinetic energy in the special case where it's an elastic collision. So this is a special case. So when you take both of these ideas and combine them, we're able to predict the final speed of mass 1 and the final speed of mass 2 just based on the initial speed of mass 1, or again we're assuming this one's at rest, and the individual masses. So here's the final speed of mass 1. So there's a couple things to notice. If mass 1 and mass 2 are equal to each other, and you'll see this in the collision lab, mass 1 and mass 2 are equal to each other, mass 1 comes in, there's a collision. If their masses are the same, mass 1 actually stops, right? Mass 1 is equal to mass 2. The final speed of mass 1 will be 0. And then mass 2 heads off. Now, if their speeds of their masses are the same, mass 1 and mass 2 are equal to each other. If this one comes in at 5 meters per second, it'll stop, and this one will leave at 5 meters per second, and you'll see that in the lab. So this equation will help you with part A, and this equation will help you with part B. C and D, again, refer back to chapter 9 when we talked about those stick-together, completely inelastic collisions. And finally, 1047, an 1,100 kilogram sports car accelerates from 0 to 31 meters per second in 13 seconds. What is the average power of the engine in kilowatts? So power is how fast you can do work, how fast you use energy. Okay, so from the mass and the speeds, we know that there's a change in kinetic energy, and this happens in 13 seconds. And we want to know what's the average power of this engine. All right, let's sketch this. Okay, so here's what I know. Mass of the car goes from 0 to 31 meters per second in 13 seconds. And how much power do we have here? And you'll have to turn it into kilowatts. So a watt is a joule per second. Okay, don't forget that, watts, perfectly good units, but what does it really mean? It means how fast can you do work, how fast are you using energy, joules per second. Okay, so the amount of work done per time, and the work here is going to be the change in kinetic energy divided by the time. And the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. We know all this stuff. And then divided by the amount of time. So you'll see that this is joules per second. This will come out in watts. And the answer, Mastering Physics actually wants it in kilowatts. So, 1,000 watts is a kilowatt. All right, if you have any questions, email me. It's a long assignment, but I know you're up for it. Okay, talk to you soon. Bye.